Okay, so hello everyone. Thank you for coming. I'd like to welcome you all to the second Plasma-PEPSC webinar that we'll have this year for our project. So I have the pleasure to introduce our speaker today, Mehmet Yusufelist. He completed his bachelor's degree. He completed his bachelor's degree. Sorry about that. He completed his bachelor's degree and master's degree in electronics and engineering and robotics. He worked in research and software engineering in the motor industry and also vision robotics companies in Germany and Netherlands and Turkey. And he's currently working with CASUS right now as beginning this year, 2024. He's currently a research engineer and contributes a lot to Alpaka. So without further ado, Mehmet, you have the floor.
Hello, everyone. Thank you for participating. In this presentation, I will initially introduce Alpaka generally, then I will go over an Alpaka program and explain it step by step. Lastly, I will give you some more information about Alpaka, like performance of Alpaka, contributors, and future plans of Alpaka team. Alpaka is a parallel programming library. As you know, you can accelerate your code by exploiting your hardware's parallelism. It's an abstraction library independent of hardware ecosystem. With Alpaka, you can create portable code which runs on different CPUs and on CPUs. Alpaka is open source and open to contributions. If we just go over the list of top HPC systems, we can see that hardware ecosystem is quite heterogeneous. The first one in the list, Frontier in USA, is using AMD GPUs. Aurora is using Intel GPUs. The third one, Eagle, is using NVIDIA GPUs. Fugaku in Japan is using CPUs, which are actually CPUs with ARM architecture, and Lumi in Finland is using AMD GPUs. And these different vendors propose different programming APIs, of course, and they are also using different colors as a part of maybe their brand building strategy. Hence, without Alpaka, the hardware ecosystem is rather heterogeneous. HPC platforms are not interoperable, or in other words, programs are not portable. Alpaka provides one API to support all different GPUs and CPU backends. Abstraction of the underlying hardware, but not hiding. Compiler and operating system is the main approach of Alpaka. For example, Alpaka does not have a default device. Built-in functions, language extensions, or a default stream or null stream, like in HIP or CUDA. It is easy to change the backend in Alpaka code. Alpaka code directly uses vendor APIs, produces the same code that a vendor API would generate. Hence, Alpaka has zero abstraction overhead for kernel execution. Supported GPU backends are HIP for AMD GPUs, CUDA for NVIDIA GPUs, and SYCL for Intel GPUs. Of course, SYCL is used for other GPUs as well. Alpaka users can use vendor profilers and debuggers for their Alpaka code directly. Supported CPU backends of Alpaka are OpenMP, threads, and TBB blocks. And Alpaka allows heterogeneous programming using different backends in a synchronized manner. Is possible with using Alpaka, actually. You can find us on GitHub. The GitHub includes full source code and many examples and an issue tracker. The documents pages are at read the docs, and read the docs includes installation guide, cheat sheet, and information about Alpaka abstraction model. Alpaka project group link at GitHub contains all Alpaka-related projects, documentations, and samples. Alpaka-related projects include Vicuña, Kupla, Llama, Bacteria. And among those projects, Kupla is an interface to Alpaka for easy porting from CUDA to a C++ code, which uses Alpaka. And another project is Vicuña. Vicuña is it's an API for Alpaka for using high-level algorithms like reduce or transform, because Alpaka is a rather low-level parallelization library. And lastly, Alpaka uses Mozilla public license. Programming with Alpaka, Alpaka is a C++ only library. Alpaka is written entirely in C++ 17. In a short time, we will be using C++ 20 features, and we will be starting compiling on C++ 20. It is a header-only library. No additional runtime dependency is used. The only compile time dependency is actually boost. Including the header file alpaka.hpp into your CPP code will be enough to use Alpaka. Alpaka supports a wide range of modern CPP compilers. All compilers we know can be used by Alpaka code, and it's portable across different operating systems. Actually, every commit on Alpaka code is tested on different operating systems and different compilers. I'm going to go over fastly on installation and examples. The first step is installing dependencies, of course. Alpaka requires boost as a compile time dependency for compilation. For the configuration of the build system and compiling CMake, compiling CMake is needed, although CMake is not a must. Depending on your target platform, you may need additional packages. For example, CUDA, ROCm, or Intel One API toolkits might be needed for different GPUs, of course. After installing Boost and CMake and, of course, compilation tools, you don't need to install Alpaka files to compile the examples. We can just compile the examples and run them. In compiling examples or any program which uses Alpaka, setting CMake variables are very important. The user needs to configure the build with setting CMake variables according to his system. These are actually backend settings, and these backend settings doesn't mean the user has to use these backends in the code, but means they are available and can be used by the user. After building using CMake --build, running all examples by ctest example command or all tests by ctest test command is possible. And installing Alpaka is rather straightforward. Compilation is not needed, just two steps are needed, configuration and installing. Notice that you don't need to set CMake variables depending on your system for installation. You can just set your CMake variables representing the available backends at your system at the executable level, namely while compiling your examples or while compiling your project. Creating your first Alpaka project can be achieved in two ways. First way is creating your CMake lists txt file and your code file in a directory you choose. And I'm just going to summarize this slide. Secondly, you can just copy one of the examples as a directory and change the code a little bit. The important point for both cases is that select all available accelerators while configuring the build tree by CMake command. Your code will be portable between those selected backends. Before moving on a small Alpaka code, I would like to talk about basic concepts of thread parallel programming. Alpaka uses grid block thread-based parallelization model. The model is instantiated differently on different processors because of cache size and the cache speed, the synchronization mechanism, or simply the difference between CPUs and GPUs. For example, GPUs have many cores but small cache sizes. On the other hand, CPUs has fewer cores with large cache sizes. By using grid block thread abstraction, the execution can be optimally adapted to the available hardware. Secondly, the thread parallel programming, by the thread parallel programming, it is meant that large number of threads should run on the same code. This code is called kernel on different data in a parallel manner. Lastly, indexing of threads is needed for thread parallel programming. Each thread should work on a different data portion or do a specific task. Therefore, a thread index is needed. There are three terms I would like to describe. The extent means the sizes along each dimensions. In 3D, for example, extent is a 3-item vector of depth, height, and width. The term dimensions means a set of dimension names, although in daily usage, daily English, we use dimensions as the extent, but here I will use as a set of dimension names, and number of dimensions is the size of extent vector, maybe. Yeah, the code example will be on vector addition problem. We are planning to simply add two vectors in a parallel and portable manner, of course. Typically, for parallelization, we need to divide the calculation of the vector C into parallel summations. That means we need to map threads to the data. In our solution, as you can see on the graph, a one-to-one mapping, actually an identity function between thread indices and the data indices is used. Thread 0 will sum A0 and B0 to find C0. Thread 1 will sum A1 and B1 to find C1, and so on. The second issue in thread parallel programming is how to select or define the grid block thread parallelism, or in other words, determining the work division in Alpaka terms. In this representation, we have m blocks in grid, and each block has 4 threads. Therefore, grid block extent is m, and block thread extent is 4 for the sake of simplicity of the drawing. Vector addition code steps are not difficult to guess, as you might guess. First step is firstly create the kernel, then decide where will the parallel and non-parallel parts of the code run, then decide how to parallelize, find number of blocks and threads, allocate host and device memory for A, B, C, and fill A and B vectors with data, copy the memory to the device from host, run the kernel, then copy the result, which is C vector, back to the host. These are the steps. And now I'm going to define Alpaka kernel. Kernel contains code that is run by each thread, and kernel knows the thread ID, which is instantiating the kernel itself. Alpaka kernels are, as you see, functors. namely structs with specifically implemented function operators. Arguments of the function operator can be pointers or trivially copied types. Here, arguments are A, B, C pointers, and the size of each vector. Alpaka function ACC constant written in capital letters is required for kernels and functions called by device. ACC is a mandatory first parameter for the kernel, and its type is the template parameter of the function. Alpaka kernel is agnostic to the device details, which makes it a really generic code. As you see, Alpaka is very low level and transparent. The term abstraction usually is associated with being high level, but Alpaka is actually low level, although the abstraction of the Alpaka is very strong. One can access to the thread index directly as in heap or as in CUDA in Alpaka kernels. Obtaining the indices of threads or blocks is easy in Alpaka kernel thanks to usage of function templates. Using a single function, getIDX function, with different predetermined template arguments would be enough to get the thread index in grid or in block, or the index of block in the grid. For example, the thread 1.4 of the block 1 would have a grid index 1.9 because it is on the second row with the index 1 and the 10th column with the index 9. And note that Alpaka grid and Alpaka threads types are used as template arguments. Same thread will have a thread block index 1.4, which shows its coordinates with respect to the block. And block grid index for that specific thread will be 1 because it is the block with index 1. The second step is selecting the accelerator platform and the device. Now we can design the code part that will not run in parallel, namely the code that will run on the host device. Initially, selecting one of the predefined accelerator types or backends according to your system is needed. Your system, for systems using GPUs, there are 3 accelerator types. For CPU backend, there are 4, and for the FPGA backend, there is an accelerator type defined. In this example, ACC GPU CUDA RT, namely GPU CUDA backend, is selected, as you see from the highlighted line. But you can easily change the accelerator type in the code, and then the code will run the kernel on another backend. It is really easy. Accelerator is a type that's only instantiated on device, not on the host. On the host code, it is only represented as a type. An instance of device is, of course, needed. Why? Because on the host side, we are going to allocate buffers to the GPU, for example, or copy data from host to device. Therefore, a device instance is needed, and it is created by using ACC type. For easy management of physical devices, Alpaka has a device data structure. The third step is how to parallelize. How to parallelize means how many blocks will be in the grid or how many threads each block will have. There are 2 ways in Alpaka. The parallelization model or work division can be selected using an Alpaka function getValidWorkDiv, as you can see, it is highlighted, which takes the full grid extent as an argument and divides the given extent into blocks. It takes namely a massive box of threads without any subdivision and divides this box into thread blocks. Elements per thread is another input used for the function. Elements per thread extent is a sub-indexing which could be assigned to each thread if each thread needs a number of additional sub-indices or an extent. And this is usually taken 1 in our codes. The generated block size by the get-valid worker will be inside the allowed limits, which is usually 1024 threads per block for GPUs. There are additional inputs which are not used for get-valid worker function here. For example, we can ask to the get-valid worker function generate blocks with equal extent, with equal dimensions. Then the extent dimensions will be equal. Secondly, work division can be just defined by the user rather than using a function. In that case, 3 vectors, grid block, block thread extent, and the thread element extent should be defined by the user. You can determine it according to your experience or trial error. Yeah. For allocation of memory, Alpaka buff type is used. It is a multi-dimensional dynamic or runtime size container. It contains memory address, the extent of the data, and the device. Since the buffer knows the device to which it belongs, it is easier to use in heterogeneous environment. And compared to CUDA, for example, memcopy, it is much easier to copy Alpaka buff because it knows the device. Alpaka alloc buff function allocates memory to the given device. Creating queue is important. Alpaka queue is created by using the device instance and the accelerator types. Here it is CUDA GPU. Queue is similar to the stream construct in HIP or CUDA, but Alpaka has no default queue. Alpaka philosophy of Alpaka is not hiding, therefore queue is explicitly created. Alpaka queue is always first in, first out, and everything is sequential inside the queue. As you can see, queue is used in memcopy and kernel execution. Hence, we are sure that everything will be completed in order because they are in the same queue. 2 queue types, blocking and non-blocking, are available, which is relevant if you want to have 2 queues. Actually, we have 1 queue here, therefore blocking and non-blocking properties are not relevant. Blocking means the execution of task blocks the caller. In other words, when a task is enqueued or executed, the calling thread, here the host, is blocked till the end of that task, that operation. If you create an unblocking queue using, for example, CUDA GPU accelerator type and then another non-blocking queue using an AMD accelerator type, HIP GPU accelerator type, host could execute on the first device without being blocked and could execute a task on the second device. Therefore, queues can be used, non-blocking queues can be used for this scenario. Yeah, that is the queue concept. Copying data vectors to the device is done by Alpaka memcopy. Actually, memcopy copies the data at the buffer passed as the second argument to the buffer passed as the first argument. As you would see in the highlighted memcopy call, only the buffers allocated to host and device are given to function memcopy without stating at which device they are allocated, or their size is not given because the device information is inside and the size information is inside the buffer data structure. Alpaka view is used to adapt existing memory if we already have an STL vector filled with data at host, for example, or any other contiguous container, SYCL container. We don't need to create Alpaka buff for copying. Getting a view of existing STL container would be okay. So if you say I'm used to using SYCL containers, what I will do, you can just use them till you need the copy. You need to copy them to the device. You can use STL containers. Then you can switch to STL view before copying. Last two steps are executing kernel and copying the result back. Kernel initially is executed or actually enqueued in a queue, and result is copied back to the host. To execute kernel, exec function is used. Q, workdir, kernel instance are first three arguments of exec function. The rest are the kernel arguments. As you see, only C++ standard kernel calling mechanisms are used compared to, for example, CUDA. This is pure C++ function call. Since everything in the queue is sequential without being blocked, and we use the same queue for two operations, we are sure that there is no problem of synchronization, and I mean the exec and the memcopy. So vector addition code looks like this. If I summarize, there's a single header, which is Alpaka HPP. This part defines the kernel. Then we are selecting the accelerator and the device according to our system. It was a GPU CUDA for this example. Then we decide the parallelism, what will be the work division by using getValidVector. Then we are getting the host device instance because we are going to allocate memory and copy to the GPU. Allocating memory for host and for the device are done by allocbuff and initially creating buffers. And buffers can be filled like filling any other contiguous array. Copying vectors to the device is done by Alpaka memcopy, and kernel is executed. Then the result is copied back to the CPU by again using memcopy. Some programming tips I'm going to go over shortly. If you want to pass multi-dimensional data to the kernel, because we said at the beginning that pointers and trivially copyable types are used, are passed to kernel, please use MD-span. If you don't use MD-span and you want to pass your data as a pointer, multi-dimensional data as a pointer, you will need to take care of alignment pitch values. There are many examples. On GitHub, you can check how to use alignment and pitch for these kind of problems. To increase performance, using shared memory and constant memory of GPUs are among Alpaka features. You can use shared memory and constant memory of the GPU, and you can increase your performance. A kernel can be run directly by exec function or can be enqueued as a task. This is a specialty to synchronize better. Vendor-specific profiling and debugging tools, that's really important, can be used on compiled Alpaka code, like ANSYS RockProf can be used directly because Alpaka builds down to the same executable code with the vendor API. If you debug GPU code, try to compile your code for CPU and use CPU debugger tools. For some types of bugs. This is a useful technique. Since Alpaka is an abstraction, you can easily change the backend. And why we don't change the backend to solve some bugs? Therefore, for example, GDB can be used if CPU accelerator is used during the compilation. Inside Alpaka kernel, you can use printf, but you should not use stdcout for GPU backends. And for unused number of dimensions in Vertiv, use one. These are simple tips. Performance of Alpaka. A study for understanding the performance of Alpaka was carried out by Alpaka contributors and maintainers at CERN. 3 parallel programming tools are compared. Alpaka, the first one, a similar abstraction tool called CASUS and CUDA. The 2 graphs on the left show the GPU and CPU utilization. In the case of mean GPU utilization, performances of 3 tools were similar, as you can see on the leftmost graph. But the CPU utilization of Alpaka was much better against CASUS and almost the same as CUDA. And the 2 graphs on the right show the peak memory usage, and the memory usage of Alpaka was much better for the GPU and slightly better for the CPU compared to CASUS, and it is very close to Alpaka actually, CUDA performances. Yeah, the performance analysis I have just shown you was done by CERN in 2021. Of course, an updated study is needed. We are planning to create benchmarks for Alpaka in a short time. Therefore, these kind of studies will be done again. I would like to talk about Picon GPU project. Picon GPU project is one of the most important users of Alpaka library. It is particle in cell code and mainly implements laser plasma acceleration. It is run on some of the fastest supercomputers. The graph shows how the performance of Picon GPU scales as the number of nodes grow according to the test performance performed on Lumi supercomputer in Finland. In the first graph, the problem size increased with the number of cores. In the second one, the problem size is fixed. Only number of cores are increased. Of course, in the second graph, we can see that there's an underutilization of capacity. The term GCD means graphics compute die. And in Lumi, there are about 2,900 nodes. Each node has 4 AMD GPU modules, and each GPU module has 2 dies. Therefore, there are about 30,000 dies on Lumi. How to start using Alpaka? Please don't try it initially on CUDA because Alpaka is already low levels. Use Alpaka directly by using examples and the cheat sheet. But if you already have a code base in CUDA, a rather simple code base would be better, I think. Converting to Kupla can be a fast solution to benefit from Alpaka features. Kupla is one of the softwares in Alpaka group. I will just introduce some of the features of Kupla. How the CUDA code can be converted to C++, portable C++ code. Initially, user needs to change the suffix CU of the CUDA source files to CPP. Then the include directive, include CUDA runtime H directive should be removed. and other include directives for the CUDA specific include files should be removed. And the user has to include the file CUDA to kupla.hpp. That's the only file needed. As you can see, CUDA and kupla code is quite similar. CUDA kernel function is converted to a kernel functor. Kernel call in kupla needs kupla kernel macro. As an example, the shared memory declaration needs shared memory function in kupla, and a 2D array in shared memory is achieved by a kupla array of kupla arrays. Here, two kupla arrays are inside each other. I would like to talk about community and long-term support of Alpaka. Partners using and contributing to Alpaka are actually 4 institutional partners. CERN is a very important user and contributor of Alpaka. DLR is using Alpaka, but their codes are not on public domain. HZDR is an important user by creating Picon GPU and by directly contributing to develop and maintain Alpaka. And lastly, Helmut Centrum Berlin has recently started using Alpaka. On the other hand, since Alpaka is a part of strategic Helmut's program-oriented funding roadmap from 2027 to 2034, a long-term support is already secured for Alpaka. Okay. As a summary, I can say that in HPC world, multiple hardware types are available from different vendors. Platforms are not interoperable. Parallel programs are not easily portable. Alpaka provides one API to support all different GPUs and CPU backends. Alpaka provides abstraction but not hiding of the underlying hardware, compiler, and operating system. Alpaka does not have a default device, built-in function, language extensions, or default streams. It is easy to change the backend in code. Alpaka code uses directly vendor APIs, produces the same code that a vendor API would generate. Alpaka don't emulate anything. Alpaka users can use vendor profilers and debuggers for his Alpaka code. Therefore, Alpaka provides zero abstraction overhead. There is no overhead, actually. If you use Alpaka, please cite one of the following publications. Thank you for your attention. And please feel free to contact us for any of your requests or questions about Alpaka. It doesn't matter if it is an installation issue, a bug, or a performance problem. I am also willing to do a hands-on session on Alpaka programming if there's an interest. Please let us know. Now we are going to move on to discussion session. Before moving on, I would like to ask to Alpaka team if they want to add anything, if they want to share anything.
All fine.
Thank you. Are there questions? I haven't been able to read the chat.
Yes, so thank you so much, Mehmet. That was a very complex and detailed presentation. So we want to open the floor now for some questions. Anyone have any questions? Okay, so I see Marcus.
Yep. Hi. Thanks for the presentation. Just a quick clarification question. Alpaka itself needs to be compiled with CMake, but does it make any assumptions about what then the actual use code is compiled with?
Yeah, Alpaka. You should set all the available systems, all the available APIs and or backends in your computer, in your system, as a CMake variable, I mean, you should define all accelerators just before compiling the code. That means you should not use each of them in your code. For example,
Yeah.
you have an AMD accelerator and
no, what I meant
GPU
was that
NVIDIA. Sorry.
what I meant was that we don't use CMake. We use just regular GNU Make. Is that all right?
Yeah, I can jump in, Mehmet. I can jump in. Yes, the preferred way is using CMake because this has the advantage that many compilers have different problems to compile code, and we ship a lot of workarounds for some flags and so on with specific for the compiler version. But nevertheless, if you really have your own build system, like CERN has an old build system, or you use Automake or something like that, you can use Alpaka on a we call it standalone, a standalone way, where you have for each accelerator and header file you can include, where a few defines are set, how we describe that an accelerator is enabled, that you use, for example, CUDA or OpenMP as a backend, what normally is done by CMake. And you need to then to ship the correct compiler flags, for example, how to set the architecture you like to compile for. For example, for CUDA, you need to set the SM level, or on Rockemit, it's a little bit different. You need then to be aware about it, and then you can use it also without CMake. But CMake is our preferred way, but the other way is open too.
Thank you very much.
Yeah, you're welcome.
Perfect. Thank you so much, Marcus. I believe there's a question in the chat. Just check it. I think, Stefan, you had a question in the chat. Are you able to ask the question? I wonder if he's still in the call.
What about the Llama? I've understood it also uses multi-dimensional array. What will it be used instead of MDSpan in the future, or how does it work?
For those who heard the name Llama the first time, or associated with I think Facebook AI project, which is also called Llama, and maybe there are several other Llama projects in the world. Our Llama project is low-level array abstraction. I don't know the full term of that. So what it is doing, if you have a container of structs, you can lay out the structs differently. The easiest one is a struct of array or array of struct. This makes already, maybe depending on the architecture, a huge difference. And then you have also mixed types that you can say, okay, I have a struct of array of struct of array of array of struct, or something like that, really complex. And this is something you can model with Llama, and you can same like you can use Alpaka for abstracting the accelerator. You can later on in Llama change the design of your memory, the byte level, how it looks on byte level after you wrote a program. You write it against one API, not one API, a single API, and later on you can try different layout schemas and check what is the best for your architecture for the performance. This also provides access to multi-dimensional arrays, but it is not substituting MDSpan. MDSpan is a little bit on a different level. So MDSpan is only handling n-dimensional arrays. It is not doing some abstraction for you that you can later on, for example, say, okay, if I have, for example, if I have an image with 4 color channels, that I have all 4 colors in the memory contiguous, and then the next color, and then you change the layout that it is separated. So MDSpan is for scalar types. You can also put in a struct or something like that, but it is not made for separating the components of your struct. So it is it has maybe an overlapping of a feature set, but it is more than less something like a reflection on your data, and then that you can also lay out your data differently. So it will not replace MD-SPAN, or will not also not be replaced by MD-SPAN. And I think Llama also has an example where MD-SPAN is used together with Llama, but I'm not fully sure. Is it clarifying a little bit the question?
Yes, thank you.
You're welcome.
Yes, and I think, Stefan, you had another question, I believe, regarding the downside of Alpaka, I believe. Do you want to back the question?
This is Leon's question.
Yeah.
Oh, that's Leon. Okay, Leon. Do you want to say, Leon, you have a question? Okay, maybe we can answer that question.
Okay. Do you like to repeat the question, or?
Yeah, I can do it. So what are the downsides of Alpaka using only features available in all backends, for example, the emulator and special features, for example?
Is this question pointing to the point that, for example, on CUDA, you could use cooperative groups inside of the kernel, where maybe on a CPU backend you can't use it? Is it in this direction, Leon?
I think he's on mute.
Okay, I think it is pointing to that question. Yes, so there are some features where different vendors have special features we currently can't support in Alpaka. We are always on the way to implement new features like cooperative groups inside of the kernel. We also like to implement as soon as possible. If you have something like that, then you most likely on the, I would say, 2 or 5% of users where you really look already in the top notch of the performance. So you are very near to writing your PTX code or your assembler code by hand. And if you're on that level, yes, that's a problem. You can't use then Alpaka directly to describe this feature because the feature is maybe not usable inside of the code. But in this case, there's still the possibility in Alpaka that you write a specialized kernel only for a given accelerator. So if you say, okay, in CUDA, I definitely know I can use cooperative group and I like to write native CUDA code, then you can say, okay, my struct is only for CUDA, for my CUDA accelerator, how we name it in Alpaka, do native CUDA calls only in this kernel. Then you are free to do it. And if your queuing of this kernel looks equally than for all other accelerators. But you need a specialization, was had also the downside, what we have currently in many code bases, which are not using Alpaka or any other abstraction library, that you then have several versions of your kernel, and this is normally what you like to avoid. But luckily, Alpaka is open source, and you can always contribute back new features.
Oh, perfect. Thank you so much. Yeah.
I would like to add a point. Task graphs and cooperative groups are two features we are planning to add to Alpaka, but those features are missing currently, as it is mentioned. Thank you.
Thank you so much. I see a question from David.
Yeah, thank you. First of all, Mehmet, very much. Thank you for this presentation. I have a very simple question. Maybe not very professional, but still. I mean, for us, main problem is interaction between GPU and hosts. So does Alpaka somehow improves and degrades interaction in speed or in memory size, or maybe the data size transfer with hosts?
So I'm maybe sorry that I jump in.
Please.
Alpaka cannot be faster than the vendor API. So if you call a CUDA mem copy, Alpaka will do exactly the same under a different name. Also, most likely without any overhead. We only translated one-to-one, for example, in this case. And Alpaka is not magically doing something. So Alpaka is not an implicit optimizer for anything. It's really low level, the same as you would write CUDA or HIP or OpenMP, and you really say, okay, let me transfer this contiguous chunk of memory, or let me transfer this contiguous chunk of memory, but with a stride in between. And then Alpaka is exactly doing what you say. So if you say do it wrong, Alpaka will do it wrong. It will not magically optimize everything. This is a complete different topic. And this is something, if we would ship something like that, we would put it as a new library or part of Alpaka, but we would put it on top of Alpaka because it is orthogonal to using the accelerator. It's only an optimization, so finding better parameters or something like that.
Okay, thank you. So it does not influence. Okay, thank you.
Yep, you're welcome.
Okay, any other questions? Yeah, so I have one, just a quick question. It's regarding I think one of your slides, you have so you can maybe go to the slide, the one where you said for programming tips, not programming tips, sorry, regarding how to start using Alpaka. I believe that was slide 28, I believe. Yes, so my question here is that I was just looking at the slides. Alpaka is similar to CUDA, it seems so. So I know that you say go for persons to go directly to using Alpaka. So if someone is really used to using CUDA, is that the best way to learn Alpaka, or directly just learn Alpaka? Because it seems very similar to CUDA.
So it depends a little bit. So if you start a new project, then definitely start directly with Alpaka. If you have already a large code base with a large CUDA code base, explicitly a CUDA code base, then Coupler can be the easier choice to try it, because we could hijack the CUDA naming and you can still keep all your API function on a host side, and Coupler will automatically translate it to a coupler equivalent function. So CUDA mem copy will then be a coupler mem copy by a define, for example. This is how it is implemented. And this is a very fast way to jump into the coupler world. I think, Mehmet, you have in the backup slides an example. Is it correct? For coupler?
No.
Okay. Then I have something wrong in my mind. But in the end, on the coupler website also is described. You need only to change a few things, but you could also use Alpaka directly in a mixed mode with existing CUDA code. So create your device with the Alpaka functions. How do you get your device? And then still keep your native API calls in. It is a little bit dangerous. You could make an error or so, but you can port a single kernel to Alpaka and test it first in the environment of all your other CUDA kernels, for example. But then you cannot change the accelerator to something else than CUDA, because you need to have all the data movement. But even if you have a CUDA code base, Alpaka is the preferred way to start with that. But if you have a slightly different interfaces, a little bit more you need to describe in the beginning. You need to say, okay, what is my accelerator type? What is my dimension of an accelerator? What is the index type for the accelerator? Where in CUDA, the index type is, or in Coupler, it is also defined. In Coupler, it's integer. In CUDA, it is nowadays a size T type, so 64-bit. The interface is a little bit smaller in Coupler and CUDA, but I would still prefer or would advise you to use Alpaka. It is really not really different to CUDA.
Yeah, that's what I was wondering. Yeah, seems so.
I just would like to add one point. If someone is good in CUDA and creating CUDA kernels, and for him, it's not going to be a serious problem to create Alpaka kernels. Therefore, I mean, the other host code, copying or creating buffers, or those parts are easier in Alpaka, and Alpaka is more transparent. Therefore, using, for example, a CUDA example, kernel code and converting it to Alpaka is easy. and host code part of Alpaka is easier, I think, than CUDA, in my opinion.
Okay, thank you so much. And I have another question I have. So on slide 17. So regarding the different backends, I believe you're at slide 17.
David, could you change the slide?
I think, Mehmet, you could change the slide. Yeah, 17. Yeah, perfect. Yeah, so I had a question here because I noticed that you have the accelerator GPU, I believe SYCL Intel, and the other one, FPGA SYCL Intel. So I believe the naming Intel, was it when you first had that in that backend, was it dedicated towards Intel compiler, or it was just something, the naming convention?
It is for, if I remember correctly, I'm not as a SYCL expert, it is for the one API you need as requirement for that. So SYCL is only an standard.
Yeah.
And there are different implementations, so the vendors are free to implement it. And the most advanced implementation currently of SYCL is the one API implementation, where it is nothing else than SYCL, plus also some small extensions, and they bring also new stuff into the SYCL standard. Then Intel bought a few FPGA vendors. I think, I don't remember the name. And the other one was bought by AMD, but I think they don't have a SYCL compiler anymore or so. And then there is the Open Compute, what is the former HIPSYCL. And we currently do not test HIPSYCL. We currently test everything with the one API SYCL version, because it's the most advanced, runs on several accelerators.
Yeah.
And therefore the name Intel is in, because it is shipped by Intel.
Okay, perfect.
So it's also for Intel GPUs at the moment, because I don't. Okay, there you can compile it to NVIDIA GPUs, AMD GPUs. This is something we currently not testing. SYCL is quite new in our software stack, and we used it already with Intel GPUs, with other GPUs. It's not well tested.
And I think I have one last question, and then Marcus, I'll give you the floor. So I didn't hear any mention of Fortran, because does Alpaka, do you have any case where Alpaka is implemented with a Fortran code? Because we have some of the projects, some of our members, they have Fortran, they use Fortran, and then there's other codes for, let's say, for example, a Jurek or a Machine. In this case, they would want to use Alpaka. What will be the best recommendation, or you don't use Alpaka in this case?
My recommendation is switch your project to C++ for sure.
Oh, I see.
Without blaming anyone, Fortran is, in my opinion, not really developing a lot in many core programming. So there's the Fortran compiler from NVIDIA, I think. Fortran or something like that.
Fortran, yeah.
But it was coming very late after you had the C interface for CUDA, and I'm not using it, but I haven't heard it is working, but not everything is working. So we do not support Fortran, because we really need C++, because we ship around C++ objects, and this object have all our context descriptions that we need to know where we are, which math functions we can use, and so on. And this is not possible with Fortran. It would be in principle possible that someone is writing a C interface to our C++ objects, and then you could use it in Fortran. I don't think that someone likes to do something like that. So that's something we definitely say, no, we can't support it. If someone likes to do it and know how to bundle C or C++ with Fortran together, it would be a nice project, and we are open for contribution. But from our side, we have our code bases all on C++. So C++ 17 at the moment with the latest release. The next release will also be C++ 17 of Alpaka, and then we like to switch to the minimum of C++ 20.
Yeah. Okay. Perfect. Thanks for that, Marcus. in the interest of time, yeah.
Yeah. That previous slide reminded me of something I thought of earlier. It mentioned that the host parallelization supports OpenMP 2.0, which is, a bit long in the tooth. And newer variations of OpenMP include, for example, support for the SIMD pragmas to support CPU vectorization. What's your roadmap on that, if I may ask?
This OpenMP 2.x means 2.x plus. So we support also newer versions. You can also use OpenMP 5. But what we are not supporting is OpenMP offloading. So how you can go to GPU. We supported it in the past. We removed it because there are a lot of problems with the compilers and so on. It was no fun anymore. And we have all the native vendor APIs, how we can tackle different architectures. So we currently do not see an benefit of having the OpenMP offloading, but you can still use OpenMP 3, 4 or something like that for your CPU accelerator, but not for the GPU accelerator.
Okay, yeah, I absolutely agree. OpenMP offloading makes no sense when you've got proper GPU code, but this SIMD functionality was what I particularly was interested in. But good to hear that you've got the support for that.
You can use it, and also if you use, for example, OpenMP 3.5, where the native atomic functions was extended, then also Alpaka is internally more efficient if you use, for example, atomic functionalities, because OpenMP 3.5 ship better atomics that you have more native atomics, for example, that you do not need to emulate everything with the atomic CAS or something like that. But yeah, it's a legacy naming. Everything newer than OpenMP 2.x is supported.
Good, thanks.
Maybe also comment on this. We are also looking at a moment how we can improve our kernel language to support better SMID, and maybe if it makes sense, some implementation using from OpenMP. Maybe in the future we rise the minimum requirements for OpenMP. At the moment, this is only the minimum which what you need.
Okay, great. And just to close, I think we went over. It's very interesting. So just to make sure, Alpaka, it will be more as a backend, right? So if someone has a project, a code, for example, in C or C++, and they don't have, like, for example, GPU programming, they would have to change their code. They'll have to do some structuring. What most likely what they'll have to do will be the first approach for that project or that team. And then the second last question before we close will be is that will Alpaka be 100% of the code? So would that team have to change their code completely to the Alpaka standard? Or, for example, if you're a physicist, you want to focus on the physics, and you're a computer scientist, you focus on that. So most likely they don't want to change the code. So do they have to change all of their code or just a portion of the code to get it faster to work on GPUs?
This really depends on the state of your project. So if you come from a project which is running only on a single sequential CPU core, then you need definitely to rewrite a lot, so that your data structures will not fit, and your algorithms will also not fit, because they are not made for high parallelism, race conditions, and all of that stuff. But even if you go to native CUDA or native HIP or OpenMP, you need to change your code and most likely your data structures anyway. For all other, it really depends also on the project structure. And for that, we are always open that you contact us. We also can have a VC with you together to understand what is the state of the project, where you like to go to. And we have a lot of experience also to port older code bases to Alpaka, and I can always suggest you different ways. Maybe also something I suggested Jeremy in the past, something that you not port everything, that you go step by step and change kernel by kernel, that you can still verify that everything works, and you have really only a tiny piece of code which can really break everything, because if you have a physics simulation or something like that, your physics should still be correct, and sometimes it is not quite easy to verify everything. Many projects do not have unit tests everywhere, so and even if you have, it could be really complicated if you change something to Alpaka or CUDA even. So talk to us. We are always open to help you, to advise you some steps how it is from our side quite easy to jump into it, but very often you end up with refactoring a lot, because it really depends if you can really handle already a many core, or you can utilize a many core architecture with your algorithms. So it could also be that you need to change really your algorithms, that you need to look in some papers what solvers, for example, are made for high parallelism execution, and then you need to implement it. So Alpaka is no magic. It is not making everything faster or something. It's really a low-level abstraction how you can access different kind of accelerators, that you do not need to rewrite your code again and again for each of the architectures. So Pick on GPU is one of the examples we are writing. It shows that you can, for example, scale really to the top notch of GPU clusters we have in the world. For example, on Frontier we are running, and but it also shows a lot of abstractions we have in CMake. You need only in CMake say, or in our build helpers, only say, okay, now run it on CPU, then it's compiling everything for CPU. CERN, for example, also is using it that they ship a single binary, which is then supporting CPU or GPU, and depending on where you are, it is selecting then the right backend at runtime. But then you need to write a little bit architecture around Alpaka, because this is nothing Alpaka is doing. Alpaka gives you the possibility to choose several accelerators to write your code, that you have one kernel you can run on a different kind of architectures, and the infrastructure around you need to write by yourself. We currently do not ship something easy methods like how to write a for each, how to write a scan and reduce or something like that. We have a library called Vicuña. We are still working on make it better and easier. But at the moment, you need to write your reduce by yourself. But if you use CUDA, you would also need to write your reduce by yourself. Other libraries like CASUS may be shipping a reduce, but this is then something like calling a magic function. You can't find tweaks then in the back end. What is a reduce doing? So if you write by your own, you can really tweak it. If your reduce is doing also something different, maybe it's not very good in the software design, but maybe you can use effect of your solver or of your physics that you reduce is not a simple accumulation of something. It's maybe something more fancy or so. Then you can write it by your own, but you need to write it by your own.
Yeah, perfect. Thank you so much. And I think we went over, but it was very useful. Thank you so much, Medius. So at the moment, thank you everyone for coming, and I close the session.